Okay, so thank you, Diane, for the introduction, and welcome everybody to the week 4 of this lecture series. So I'm Enrica Mazzon, I'm connecting from Bonn in Germany. It's a pleasure to see so many people from all over the world connecting today. So thank you to those who are coming back and already attended previous weeks, and also welcome to everybody that is new today here. So the format, maybe you're already familiar, but we will have 2 lectures of 1 hour today on Wednesday. And then after this lecture, there will be a short mini problem session of half an hour. So you can stay if you want. And then there will be 2 longer problem sections tomorrow and on Thursday. So the topic of today will be introduction to Berkovich geometry. So this is a subject much bigger than what I can fit in just 2 hours. But I will try to introduce you to some key ideas. And in particular, I will try to talk about the relation between Berkovich geometry and tropical geometry. So in particular, today, we will basically see the definition of a Berkovich space, and we'll try to construct and visualize a couple of examples. So since a Berkovich space, as we will see, is a space whose points are semi-norms, let me start by giving you or recalling you the definition of what it is a semi-norm. So, okay. So we fix F to be a field, and we say that the map will be for us a semi-norm, what we call here semi-norm, if the following conditions are satisfied. So we want the semi-norm of 0 to be 0, the semi-norm of 1 to be 1. And then we want that whenever we consider a product of 2 elements A, B in F, then the semi-norm has to be smaller or equal than the semi-norm of A and the semi-norm of B. And then the third condition that we ask is that when we consider instead a sum of 2 elements A plus B, we want this to be smaller or equal than A plus the semi-norm of A plus the semi-norm of B. So this is, what I mean here today for semi-norm. But we will be particularly interested in semi-norms that satisfy some additional properties. So in particular, we will be interested in semi-norms that are not just sub-multiplicative, as this is what means the second condition that I wrote, but we will be particularly interested in those that are called multiplicative. So here we mean that the semi-norm on a product is really equal to the product of the semi-norms. Then the reason why I called my first definition, we use the terminology semi-norm and not a norm, is because we call it a semi-norm a norm where 0 is the only element who takes value 0 under this map. So in this case, we call it a norm. And then there is a third condition that I will refer today as the strong triangle inequality. That is what makes our semi-norm a non-Archimedean semi-norm. So here is when we consider the norm of A plus B, this is not just smaller than the sum of the 2 norms, but it's smaller than the maximum between the 2. So let me start immediately by giving you a couple of examples. So I think that we are all familiar with an example of a field that is endowed with a norm, a multiplicative norm in particular. For instance, so this famous example is we consider the complex number, and we take the usual norm on the complex number. So we say that the norm of x plus iy is equal to x squared plus y squared, and then we take the square root. So this is an example of a field. This satisfies all the conditions that I wrote, except the fact that it's not non-Archimedean. Okay, so now let's see a couple of examples of a non-Archimedean norm or semi-norm. So there are 3 examples that I want to recall today. So the first example, we will consider, we can take any field F, and we can endow F with the trivial norm. So here means that for any element A in F that is different from 0, because we know already that the norm of 0 has to be 0, then the norm of A is equal to 1. So you can check that this satisfied all our conditions. Then the second example that I want to mention is when we consider the rational number with the p-adic norm. So any rational number can be written as a product of a certain power of p times b over c, where we impose that p does not divide b and c. And then if we want to consider the valuation, we will remember this exponent m, but here we're working with the norm, so we will consider p at the power minus m. And then the third example, if you are less arithmetic but more geometric minded, then maybe you will like the example of C double bracket T. This is the fields of Lorentz power series with the t-adic norm. So here, by convention, we fix the norm of T to be equal E minus 1. And so it means that a general element in this field is written as a series T, an T at the power n. Let's suppose that the first non-zero element is n0. Then in this case, we will have E at the powers minus n0. So let me mention that here I choose E, but this is like more a convention. I could have taken any epsilon bigger than 1. And then this would have defined a non-Archimedean norm. So let me add just two more remarks before moving on. So the first one is that here I define a semi-norm, norm, non-Archimedean norm over a field, but you could also define them over a ring, imposing exactly the same condition. And then the second remark is that maybe you are familiar with the additive notation. So maybe you have heard about the p-adic valuation and also the evaluation associated to C double bracket T, where these two are just, one is the multiplicative notation, the other is the additive notation. But basically we can pass from a norm, from a non-Archimedean multiplicative norm to a non-Archimedean valuation just by taking a logarithm or an exponential. So this is maybe just in case you're more familiar, just keep in mind we're working with the same object. And for today, I think that for today it's better if we keep the multiplicative notation, so we work with norms. And the reason is that now that we've fixed our field, and in particular we will fix a non-Archimedean norm, we also want to study the metric associated to this map, okay? So in particular, we are interested in looking at the balls that we can define on a non-Archimedean field. So we are interested in, this is the setting now, from now on I will fix a non-Archimedean field, I will denote it K. And sorry, here I recall for you.
We have a question from someone who arrived late, and we had several people arrive late. So
okay.
The question was, a norm is equivalent to evaluation?
Yeah, that's what I just recalled. If we fix a non-Archimedean norm, that's the multiplicative notation, but then you can just define a valuation by taking minus log of the norm. Yes. Any other question? Okay. So then let's move to the matrix, so to the topology that we can define once we've given a norm. So here I recall for you what make like our case of the non-Archimedean field distinguished by the Archimedean. It's really this strong triangle inequality, and we can define as usual the notion of a ball. So the notion of a ball will be all the elements in our field K such that the distance to a fixed element, denoted here A, it's smaller or equal than R, and here R will be the radius, or strictly equal than, strictly smaller, sorry, than R. So I think that you all have the picture of how this object looks like when you consider C with the usual norm. But now let's try to familiarize of what's the shape of these balls when we work instead with non-Archimedean fields. So let's start with the trivial norm case. So for instance, you can imagine that we are working just with the complex number and we fix an element. So now I propose you a question that you can write the answer in the chat. So if we fix an element A, a complex number, what would be the ball of center A in radius 1? Okay, see already that there are a couple of questions. I just give time to people if they want to think about and also type their answer here. Okay, so what we see, I mean, I see maybe just see a couple of answers, but they're all correct. The one I can see is that this will be all the elements, all the complex numbers will be in this ball because they're all, at distance. All the points are distant one from each other. So as soon as I take the ball of radius 1, all the elements of C will lie in this ball. But then now, this is a second question. What about if we reduce the radius and for instance, we take 1/2 as the radius? What will be in this ball? Okay, I see that some people are reacting and indeed the answer is correct. So in this ball, we will only have the element A because now all the elements different from A will be a distance 1. And so if we take the ball of radius 1/2, then we will just end up with a singleton. So we've seen here that in the trivial norm case, we have just two kinds of ball. When the radius is bigger or equal than 1, then we have the whole space. While when the radius is strictly smaller than 1, we have just the singleton. So it means that what we're working with is a topological space that has a metric, and whose topology associated to the metric is the discrete topology. So that's the way you can visualize such an object, such a space. But now let's move to the non-trivial norm case. So, and let's see now, in this trivial case, we see that all the balls are or completely disjoint or that there is just, the whole space. Let me show you instead what happened when we are in the non-trivial case. So suppose that we're given two balls. One is centered at 0 and the other is centered at the point A prime. And the radius are R and R prime. With R prime, we can, without loss of generality, we assume R prime to be smaller than R. And let's assume that these two balls are not disjoint. So there is an intersection between the two balls, and I call the one element that is intersection, I call it B. Then what we can prove, and it's an elementary application of the strong triangle inequality, is that as soon as, since these two balls have an intersection, then, indeed, in fact, they are one containing the other. So let me show you, how you can prove such a statement. So suppose that you take a point X that lies in the first ball. So if it lies in the first ball, so it's such that the distance with A prime is more than equal than R prime. Then we want to prove that it lies in the second ball. So we want to consider the norm of X, but this is equal to the norm of X minus D prime plus A prime minus B plus B, right? And then now we can apply our strong inequality and see that this is more than equal than the maximum between. So if we consider the first two, we've just seen that this is more than equal than R prime because X lies in this ball. Then if we take the second two, so A prime minus B, then by assumption, B is in the ball A prime R prime. So this is also smaller than R prime. And then if we consider the norm of B, B is also in the ball of centered 0 and radius R. So this is smaller than R. And so we see that the maximum here is R. And we prove that indeed, these two balls are one containing the other. So it means that we are working in the non-trivially valued case with a space where the balls are or completely disjoint, or disjoint with respect to each other, or contain one in the other. So I want to show you the following picture. This is a picture made by Daniel Leith, and it's a picture of the valuation ring of Q3, so the p-adic number with when P is equal 3. And here, we're seeing, you should imagine this, this picture to go, infinitely upwards. But what he drew here is that basically we have smallest balls when we decrease our radius, but we can see that these balls are or disjoint or contain one in the other. Okay. So the observation that we made so far about the metric, the non-Archimedean metric associated to a non-Archimedean norm are just example of all the phenomena that can occur when we impose this strong triangle inequality. So, I mean, here I want to mention a couple of other properties. Some of them will be also part of the exercise sheets. So you will have the opportunity to work them out. But for instance, the first one is telling us that, I mean, we can even have a stronger version of the strong inequality. So as soon as we know that B and C have different norm, then indeed the norm of their sum will be exactly the maximum between the two. And then you can also see some other, some other instances of these phenomena that appear. So now that we have, so what we did so far is that we fixed a non-Archimedean norm. We studied the metric associated to it. So this is a metric over Q. It's even a metric over K. And we can also think of it as, I mean, it will also induce a topology on product of K, so K square and Kn in general. And then now, in the same way as we think of complex analytic manifold as gluing of balls that lives in C at the power n, we could try naively to construct also analytic manifold over non-Archimedean fields in the same way. So what we mean here is that we could try to do what it's called like naively Archimedean geometry by starting with an algebraic variety. If you like, just think of an affine variety. So given by some vanishing of polynomials, okay? And naively, we could try to construct an analytic manifold just by taking basically the solution of the polynomial in certain power, in K or its powers, and then try to glue them together. But the problem is that with this approach, I mean, we've seen that already the topology of K is pretty as a lot of, I mean, weird and pathological behaviors. And so we can expect that the same will also affect the structure we're trying to define. So these K analytic manifolds that we're trying to define will also reflect all the properties, bad topological properties that we've just observed. I mean, if you want to have like an idea of, I mean, how bad this space could be, you need to think that we've just seen that these balls are all open and disconnected. I mean, all disjoint and open. So we can think, for instance, that the notion of an analytic function, in some sense, would be quite different to what we what we would like to define as to be a continuous function. So the problem that we are facing is that we have a pretty unsatisfactory theory. And I mean, another way to see why this is a naive approach and is not the one we want to take is that, for instance, when we start with a variety and we take its identification in this sense, we will not really be able to recover the geometry of X. And I mean, an extreme illustration of what kind of phenomena can happen is the following result by Serre. So Serre studied compact analytic manifold defined in this way. He studied them over a local field. So think of, for instance, QP is an example of a local field. And what he proved is that if we consider compact QP analytic manifold of a certain dimension, then we only can have a finite number of isomorphism classes. And this will be just this joint union of balls at the power n. So it means that we are completely disjoint, and that we are just like, in this case, P type of P isomorphic class for all the compact QP analytic manifold. So there have been many approaches to develop a theory in order to do, give a good definition of what it is an analytic manifold over non-Archimedean fields. Let me just mention a couple of names. So I think maybe you heard about Tate theory of rigid space, or also Renault theory of formal schemes. But among the various approaches,
Question of
yes.
What did you mean by k-analytic manifold?
So with this definition, I really mean that you want to take some open balls in Q, in this case QD, if you want to define a d-dimensional Q analytic manifold, and then you want to glue them via analytic functions. So you need to think this is just taking the construction of the complex analytic manifold and following line by line the definition, just replacing C with the field K. So I didn't give here the definition of what is an analytic function, but I mean, you define it in the same way. So limit of convergent series. So you can define it in the same way. But I mean, I will not focus further because this is indeed the approach that we don't want to take, because it's the one that gives us, I mean, pathologically or a theory that is not the theory that we would like. I mean, we really aim to have a theory such that the analytification remembers a lot of information about our starting variety. We can even write passing from one to the other back and forward. Okay. So for this reason, I will focus on the Berkovich approach. And so I will now get started with what is a Berkovich space. So the Berkovich identification was introduced by Vladimir Berkovich. He started in the late 1980s, early 1990s. And the idea is that, I mean, this kind of space that we described so far, I mean, one of the bad topological property that they had is that they were totally disconnected. I mean, if you remember the first picture, we have the discrete topology, but also in the picture of the non-trivial case, you could see that, I mean, working out all the properties, you can also prove that the space K with a non-Archimedean norm is totally disconnected. So in some sense, we would like to improve and to give a different definition. And the idea of Berkovich is that in some sense, the problem does not rely on the topology that we are considering, but relies on the fact that we should, I mean, we are missing a lot of points, or in some sense, we should add more points to get a well-defined structure. So if you want to keep an analogy in mind, you need to think, for instance, when you take the line R, so the real number, and you look inside the subspace of the rational number. Then with the induced topology, the rational numbers are totally disconnected. But I mean, in some sense, the right way to fix this problem is looking at the rational number inside the real numbers. And then you end up with a nice connected space. So in some sense, in the same sense here, we want to add more points to just the points that come from our field K. And the new points that we want to add will be indeed semi-norms. So that's the reason why I started with defining for you semi-norms. And now I will explain everything in details. So let's start. So we fix here an affine variety. So for the moment, I will give the definition just for affine varieties. So as I mentioned, this is a vanishing of a set of polynomials inside A and K. So it's usually in algebraic geometry that in order to study X, we can look at the property, or we can study the functions that are defined on the variety. So in this case, the functions that are defined on our variety X are the element of the ring A, and this is a ring of polynomial in n variables, then then we quotient by the polynomial f1, fm, because these are identically 0 on our variety. So we will now give the definition of what is a Berkovich space. So I will denote this as X-an. So this is a Berkovich space associated to our variety X, or also the Berkovich identification of X. And we will do it step by step. So first, I will tell you as a set, what are the points of our Berkovich space. So here we will take as points all the multiplicative semi-norm. I will denote this bar X. So as a convention, I will denote the points both X, if I think them as a point, or with the double bar X, if I think of them as a semi-norm, but they are exactly the same object. So this will be multiplicative semi-norm on A, our ring of function defined over X, that takes value in the real positive numbers. And with the only condition, so such that when we take an element lambda of our field, base field K, we want that the norm of lambda with respect to X is equal to the norm of lambda with respect to the field K. So this is something that I will denote as we're looking at multiplicative semi-norm that extend the norm that was already given on K. Okay. Now, these are the points. Let's see what is the topology that we want to consider on these points. So we will consider the course's topology such that for any element F that is given in our ring A, we can construct a map from X AN to the real number, real positive number. And this map works as follows. So to any semi-norm or any point X, we can associate the value of this semi-norm at F. So this is a function that is basically, we are evaluating the element F. And so we ask that all these functions to be continuous in the Berkovich topology, so in the topology that we are constructing. And then to give a complete definition of a Berkovich space, we should also talk about the sheaf of analytic functions. So in the same way as we want to, in the complex analytification, we talk about analytic functions. So here, these are again, in this case, this sheaf is given by some convergent series. In general, it's a completion of our ring A. But since we will not work with this structure, because today we will just treat Berkovich spaces as topological spaces, I will not give you further details. But please keep in mind that there is also this additional piece of information that is can be really important when we do Berkovich identification and in general Berkovich spaces. Okay, so if there are no questions, we will now try to construct together a couple of examples, but let me pause just for 1 second and see if someone has a question that wants to ask or write in the chat. Okay, so chat seems to be quiet. So I will now move and try to construct together with you our first example of a Berkovich space. And it will be the example of the Berkovich affine. Okay, I see a question. Can you embed points of X sending F to F of X? Yes, you can. That's exactly what we're going to start with, because that's exactly the idea. So here, let me construct it, and then I will come back and comment on the question. But the answer is yes. So here we're fixing, we want to construct the affine line. So it means that we're fixing our space X, our variety, starting variety is the affine variety over K. And for the moment, I want to focus on the case where K is trivially valued and algebraically closed. So this will be our first example. And then, as I just said, giving a point in the Berkovich affine line corresponds to giving a semi-norm multiplicative on the ring of polynomial in one variable and fix the variable to be y. And this function has to take value in the positive real numbers and has to extend the trivial norm. So as it was suggested in the chat, the first way we can construct points is, for instance, we can fix an element A in our field K, and we can construct the norm eta A0. So this is exactly, so to any polynomial F, we will just evaluate our polynomial at the point A. So now what we have is an element in the field K, so we can take the norm with respect to K. So what happened in this case? For instance, if we take y minus a, so if we evaluate in this case, we get a minus a is 0. In the trivial norm, we say that 0 goes to 0. While, for instance, if we take y minus b, then this is sent to a minus b, and as long as b is different from a, then a minus b is an element different from 0. for the trivial norm, this is value 1. Okay, so that's what, I think this answers the question that was asked in the chat. But now let's try to construct other points, right? So let's still, I mean, if we fix an element A in K, and we fix a real number between 0 and 1, I want to define a semi-norm that I will denote eta AR, such that now our element y minus A is not sent to 0, but sent to R. Okay? So now this is another question for the audience. So what happens if we, I mean, I just give you this condition that y minus b is sent to R. What will be the norm of y minus b if b is different from A? Okay, I can see some answers. So I'm not sure that I can see them all. So I will pause for some more seconds. So I can see one answer right now, and is that it would be the maximum between 1 and R. And this is correct. And indeed, you even know what is the maximum, because here I fix R to be smaller than 1. So the maximum is really 1. So, and the way you can prove it is, again, just an application of the strong inequality, because you can write y minus b as y minus b plus a minus a, and then you can compare.
I think there's a question, can you remind us of the definition of eta AR?
So for the moment, I don't have to remind this, in that we are constructing the definition. So, so I will give it now for you. So if you want, like, the general definition will be that an element f will be sent to R at the power the order of A in F. Okay, so what is the order here? You can define the order in two ways. You can think of the biggest power m such that y minus a is dividing f. Oh, sorry, y minus a at the power m is dividing f. Or you can also think of the first non-zero term in the Taylor expansion of f at a. But in some sense, I mean, if you think, what do you mean by the, so yes, here K is order. I mean, even if I don't know what you mean by interval here, in the sense that the only, I mean, we're taking values R in, I mean, in our small r in 0, 1. So these are just the real number. Okay. So far what we define is, I mean, we define these blue points that are just associated to element in K. And now what we just define is that for any element, when we fix an element A in K, to each element R in our interval, we can define some norm. These are the eta AR. So it means that in my picture here, I can attach to each of these element in K an interval 0, 1, okay? And why I'm attaching the interval to the points is because when R is equal to 0, we get back the norm eta A0. So we can really, like, it's reasonable to attach them to the blue points, okay? And so now let's continue to our points. I mean, to construct points in our Berkovich space. So right now, if you look at the evaluation of y minus a, we send it to 0 in the first case. We send it to R in the second case, but R was smaller, strictly smaller than 1. But now we can decide to send it to 1. But as soon as we do, as soon as we do this, so what we will construct is what is called the Gauss norm, that sends every polynomial f different from 0 to 1. Okay, so as you can see here is basically, I mean, all these intervals that are parameterized by the open interval 0, 1, they indeed connect at this point, the Gauss point. So the right picture that I should draw is really like that this interval 0, 1, they are connecting here. And they're all parameterized by the open interval, right? And these points here is what we call the Gauss point. So the Gauss point, if you see, is just the trivial norm, because a way we can extend the trivial norm from K to Ky is just by, again, taking the trivial norm also in our polynomial ring. Okay? And now let me conclude the picture. So we want to see if, I mean, these are not all the points we define. If you look here, all our polynomials are all value strictly smaller than 1. So what we can also do is that for any element R.
Here we have two more questions. The first, the easy one is, can you repeat the definition of odd AF?
Yes. Okay. So here, let me define the order. So you can define as the smallest integer m such that ya at the power m divides f. So you can think that you can factorize f, and then you will look at what is the biggest factor, I mean, the power of the factor y minus a in the factorization of f. That will be the order of f at a. And then what is the second question?
Dan's pointing out, you said smallest, but you meant largest.
Yes, sorry. Yeah, okay, sorry. Thank you. Yeah, you're right. The bigger m such that, sorry. Thank you for the correction. And then, yes, I think there is a question if we are sort of constructing a cone with base, with vertex, the Gauss point. Yes, if you think in set-wise. I mean, as a set, that's basically what we are getting. But then soon we will also study the topology, and you will see that the topology that we are considering is not the topology that usually associated to the construction of a cone. Okay, but we will get to this point. Okay, let me conclude the picture. So here we fix an element R between 1 and infinity, and we can construct a norm that I will denote eta infinity R, that sends every polynomial to R at the power degree of f. And so again, here, if we fix R to be equal to 1, you will see that we get back the Gauss norm. So this infinite ray that we are adding in our picture is a ray that is attached to the Gauss point. It goes up until infinity. So here we are on element A, R between 1 and plus infinity. Okay, so just to sum up, this is the picture that we get. And these are all the points. I mean, you can prove that these are all the possible semi-norms that we can define on A that extend the trivially value norm on K. Okay.
So there's another question in the chat.
Should we think? I think that's, I mean, they're asking if they can think of the Gauss norm like the generic point of the skip. Yeah, that's a good intuition to think. In some sense, we are adding more points. Yes. Okay. If there are no other questions, now I will propose to move and try to see now the topology. But before moving to the topology itself, I have a warm-up question for you. They will, I think they will help you visualize what are the open subset in the Berkovich affine line. So this is the question. So what is the set of all the semi-norm in this Berkovich affine line whose value, I mean, when we evaluate the coordinate y, then the valuation is more than equal than 1. So I will try to give you 3 options, and you tell me what you think the correct picture is. So these are my 3 options. So the first one is just the ray that connects the Gauss point to the K point associated to 0. Okay. Then the other picture is all the other rays from the Gauss point to the K point, except the one that goes towards 0. And then the third case is when we get everything from the Gauss point except this yellow line. Okay. I will pause for a second and let you think about this question. Okay, I can see that there are some answers, and it seems to all agree that the answer should be the third picture, so number 3. So this is correct. So let me explain why. So we're looking at we are looking at the semi-norms such that when we evaluate y, this is more than or equal than 1. Then for sure we have the Gauss point because y is different from 0. So its norm will be equal 1, in particular, it's more than or equal than 1. Then we can see that, if we fix any element A, in this case I took A second, for instance, in the picture, and we consider the semi-norm associated to a point in the interval joining the Gauss point to A second, then here we've seen that the norm of y is always equal to 1. So these points will be in the set we are studying. And then the only place where our valuation will not be always equal 1, but still will be smaller or equal than 1, is the leg that joins the Gauss point to the 0 point. Okay. So now that we have this picture in mind of, for instance, how this will be, for instance, a closed subspace in our Berkovich space, we are ready to study the opens in our with respect to our Berkovich topology. So as we said, let me recall it for you. The topology that we are considering is such that if we fix any element f in our polynomial ring, okay, I can see there are questions. Are the norms in A1? Yes. So this is something I mentioned, but I didn't write. Yes, the points that I defined for you are all the points of the Berkovich affine line in the trivially valued case and algebraically closed. And you can, if you're interested in seeing, trying to prove this statement, then you should join the problem session and you will see, a guided exercise to prove such a statement. So if you take, then someone is asking, if instead of looking at the set where y is smaller than or equal than 1, we take just strictly smaller than 1, then what kind of object we take? So now I will answer, because this is exactly my example. And okay, so as I say, the topology is given any polynomial, we want the valuation with respect to this fixed polynomial to be continuous. So here again, we fix an easy one. So we just fix the polynomial y. And this means, we're saying that this maps has to be continuous. It means that preimage of opens has to be open. So the open in the real numbers are the open interval. So here I fix S and S prime. They define an open interval in R, and we're taking the preimage. So there are for sure 3 cases, right? So the first case is when we ask S prime to be smaller than 1. And this is in particular is an answer to the person that asked, just asked in the chat. So here we can see that if we fix S prime to be smaller than 1, then the kind of open we will get will be an open interval here on the leg that joins the Gauss point to 0. So this will be our open. So in particular, the answer to the question in the chat is yes. You will get I think it was like the second picture, or the first picture, I remember, the one where it was just one of the leg, but you also have to remove the Gauss point. Okay. Then the second case, so this was if S prime is smaller than 1. Then let's look at the case when if S is bigger than 1. Then in this case, we've seen that the only place where the valuation of y is bigger than 1 is in this yellow part. So in particular, we will get an open interval here on the yellow, on the leg that goes in the infinity direction. And then what about, so this is our second case. And then let's see at the third case. So what happens if, sorry, let me change color so that it will be clear. So what happens if now we look at S smaller than 1, but S prime bigger than 1? So in particular, in this case, we already know that the Gauss norm will sit inside. So we know that we will have the Gauss point for sure inside. But what you can prove is that what we get is, so we will get like sort of small intervals containing the Gauss point, but we'll also get all the other legs, because we're just seeing that all the other legs, the norm is constantly of y, it's constantly equal to 1. So, and 1 lies in this interval. So what one can prove is that this open that I just described to you, the one when we studied the preimage of the intervals, are a pre-base for the Berkovich topology. So it means that you just need to consider all the finite intersection to get a base for your topology. And in particular, what you can prove, and this also will be part of the exercise, is that the Berkovich topology of the affine line is exactly, I mean, if we look at the legs without, I mean, when we remove the Gauss point, then we have just the usual metric topology. We just have the usual open intervals. But around the Gauss point, what you can prove is that any open neighborhood of the Gauss point will contain all but finitely many legs. So in this sense, the topology we're taking here, it's really different from taking the cone with vertices, the Gauss point. It was pointed out before. Okay. So now let's move to the non-trivial value decays. Okay. So again, we will still study the Berkovich affine line. So our X will be A1K. Our ring will still be the polynomial ring in one variable. And again, we want to study all the possible semi-norm. So as you would mention before, again, if we fix an element A in K, we can again define eta A0. And this will just associate to any polynomial F. We will evaluate in A and consider it's the K value of F of A. So here we can see again that y minus A will be sent to 0 because the valuation is 0. But when we consider y minus b, then now this will not be sent all the way to A. This will be sent to A minus b norm with respect to K, when b is different from 0. But once again, we see that all the K points are indeed embedded in the Berkovich space. So here we'll have, for instance, 0, A prime, B, and C, and so on. Yes, sorry. My pen didn't write, but it was B different from A. Thank you. Now, let's construct new points that are not just the points from K. So again, I mean, here if we can still fix a point A in K, and the real number, now positive real number. And one way to define a semi-norm on the polynomial ring, that I will denote again eta AR, will be that to any element polynomial F, we will associate the sup of F of Z, where Z is varying in the balls of center A and radius R. So we can let the point vary, and then for each of these Z, we take, we evaluate the polynomial and we take the K norm, and then we take the supremum. So it means that here, I mean, for any element in K, these blue points, it means that we're adding
another question.
Is the ball closed? Yes, the ball is closed and open. So this is one of the consequences of the non-Archimedean condition, and you can prove that this ball in the metric topology is both open and closed. Yeah. Okay. So now, as I said, for any element of K, we will have a radius of, we'll have a real line parameterized by this R, and associated to each of the elements, we can define such a norm, right? But okay, and the same will also happen for the other points. So you can picture, these lines that I'm drawing, you can picture as parameterizing the balls when the radius is getting bigger and bigger, right? But then I want to remark what we proved at the beginning. So we proved that as soon as the radius is bigger and equal than A, the ball of center A and radius R is also the ball of center 0 and radius R. So we say that, I mean, why this is true? Because we're saying that two balls, as soon as they have an intersection, that they are contained one in the other. And in particular, these have the same radius. So it means that the picture that I'm drawing here, I mean, the right picture that I should draw is that these lines that they were starting from the blue points, they connect to each other. And in particular, they connect when R is equal to the norm of A. And the same also holds for the other points. For instance, this line that I was drawing here from B and the one from C, they will join each other when R is equal to the norm of B minus C with respect to K. Okay, so the right picture that we should draw is really like what is called like an infinite tree with many branching and ramification points, such that, for instance, okay, if this is like an element D, then the points where D connect to the ray from 0, it will be at the norm of D. Okay. Yes.
Is this the same as what happens at the Gauss Norm?
So what? I mean, what is this? So I think that, let me try to give an interpretation to the answer. In the trivially case, we have one branching point, that was the Gauss point. While here we have many branching points. And in some sense, yes, I mean, the same phenomena that you could see around the Gauss points now sort of appear at all these branching points. Okay, and in particular, let me also remark, I mean, how many of these branching points we have. So I mean, a branching point corresponds always to a value R that has to be a value in the value group of our valuations. So if our valuation takes, it could be dense in R, but maybe there are some element R that are not attained by the valuation, then this value will not be branching points. But as soon as the value R, there exists a certain lambda such that R is equal to the norm of lambda, then we have a branching point. And basically, locally, you really need to think of the topology look like the topology around the Gauss point. Okay. So this was, okay, here are there further questions? Okay, feel free to write them in the chat, and thanks, Diane, to interrupting and ask them loud. So what one can prove, and this is also part of the exercise, is that basically all the points that you can construct in the Berkovich affine line in this non-trivially and algebraically closed case are given by balls or by sequences of nested balls. So in some sense, I've given you all the essential ingredient to construct all the points.
We've got two more questions.
So if K is equal to QP, so be careful, QP is not algebraically closed, so it's strictly is not the case we are considering. Are the branching point indexed by Z? Yeah, this will be our branching point, yes. But in some sense, this is not precisely the setting we are looking at. And then the other question is the embedding of A1 in the identification of A1. Yes, so the blue points that I draw, these are, yeah, sorry, here I'm mixing the notation. So when I mean A, I also mean the norm eta A0. And here I'm really stressing the fact that we have an embedding of all the K points inside the Berkovich affine line. And also another question, in the trivial valuation case, the fact that the neighborhood of the Gauss point has all but finally many of the branches reflected the fact that we have in the Zariski topology. Yes, I think you can you can think of, in some sense you're thinking like 0 is contained in all prime ideals. If this is what you have in mind, yeah, I think that, yeah, you can also see in this way, yeah. What does it mean that all the points are, okay. To make this statement precise, the fact that all the points can be described by balls in sequence of nested balls, I suggest you to look at the problem sheets of tomorrow. It will be like an exercise is completely guided, and you will see what we mean here by we can use balls and sequences of balls to define all the points. But I mean, I will not give now further details, but I will just refer to the problem sheets. Yeah. Okay, so now let's also have a look at the topology. So again, the topology is the Berkovich topology. So again, we can fix a polynomial f to be, for instance, equal to y. And we look again at this our basic open, so the preimage of the intervals. So in this case, the preimage, you can like compute it precisely, but it will be, again, on the line, starting from 0 and going towards infinity. It will be given by an interval, okay? But then this open will not only contain this segment, will contain these segments together with all the branches that are attached to a point in that segment. So this is how it will look like. Okay. And also all these will be in this open U. Okay. And so in general, what we can prove about the topology will be something similar to what you already observed, is that if we fix up branching points, then an open neighborhood of the branching point will always contain all but finitely many of its branches. So exactly the same behavior that we saw around the Gauss point in the trivially valued case. Okay. So if you're curious about this topology and the property of the Berkovich affine line, that's the main subject of the problem sheet. So you can come tomorrow and you will discover much more. Yeah. So let me just conclude by looking at, today we just studied 2 examples, basically like the same example in the trivially valued case and in the non-trivially valued case. But the construction that I just described for you, it can be made much more general. So it will work for any algebraic variety. We can think of the algebraic varieties gluing of affine varieties, and I gave you the definition. But there is also like an alternative definition. This is also mentioned in the problem sheet. And then the second thing that we discussed at the beginning is that we wanted a nice topological object. So I think that already now that we draw the affine line, you can see that we pass from a totally disconnected space, the blue points, the K points, to like a nice path, connected, even path connected, even uniquely path connected space in the case of the affine line. So what it can be proved in general is that the Berkovich space has nice topological properties. Here I mentioned a couple of them. And you can even see that the property of the Berkovich space reflects the property of the starting algebraic variety X. If you heard about Gaga result when we take complex analytification, then I just want to mention that you also have Gaga result in the Berkovich analytification. So these are results that tells you that basically studying proper algebraic variety is equivalent, their category is equivalent to study their analytification with respect to the Berkovich analytification. Okay, so it really means that we can recover the property of X from the analytification. And then one last result that I want to mention is a result proved by Gruzowski and Lozer. It was first conjectured by Berkovich and proven in a couple of cases. So this is a really strong result on the structure of the Berkovich space. It's saying that the Berkovich space is always locally contractible and has the homotopy type of a polyhedron. So let me mention that the way they prove it was using model theory, but that in most of the cases, especially the second fact, this fact that the Berkovich space is the same homotopy type of a polyhedron, it can be, this polyhedron can be constructed explicitly, and this is the notion, the construction that, that we will talk about on Wednesday, and these are usually called skeletons inside the Berkovich space. So, I mean, let me just mention, I mean, what else we will see on Wednesday. So as I said, I will talk about the skeletons, but just in the case of curves, since, I mean, the main question that I want to tackle is what is the relation between the Berkovich space and tropical geometry. Of course, we'll just see some instances of the relations. And then also, I mean, I mentioned it during the lecture, please come to the problem session if you want to prove some of the results that I mentioned, just familiarize with the notion, just like, yeah, solidify this concept. We prepare exercises for all the levels. So even if you're a beginner, you will find some easy exercise you can start with. And also if you have time and you want to stay a little bit longer now, we will have a mini problem session where you can yeah, start seeing and playing with the main definition. So I think there was a question, are we assuming K algebraically closed? I think the result that I mentioned, the Berkovich results about result that relates the topology, the geometry of X to the topology of the identification do not require K to be algebraically closed. So they are really general. Okay. So I think I will stop here and thank you all for, yeah.
So let me start by just saying, before we get the questions, so people typing them now, I would like to ask everyone to join me in thanking Enrica. And you can type your thanks or your clapping in the chat. And then in a moment, we will have to have the people who, I saw there were 2 questions that came by, so we'll have to re-ask those in a moment once we've given our initial thanks. And again, we'll have a brief question period then there'll be a brief break, and we'll start the mini problem session. So.
Okay, so I can see that there is a question about the reference to Berkovich space. So I think that, I mean, if you want a reference about what I described today, so especially focus on the case of curves and starting from the Berkovich affine line and projective line, then I suggest you to read Matt Baker, maybe you met last week, Introduction to Berkovich Analytic Space. So this will treat, I mean, in details, the material that I talk about today.
The Arizona Winter School notes?
Yes, exactly, the Arizona Winter School. But yeah, I'm thinking of putting a list of references at the end of the first problem sheet, so that will be all available to everybody. I mean, if you're not right now writing down the name of the paper. So you will also find a list there. And then, can you say something about how this is generalized to non-affine scheme? Do you just exclude the result in Berkovich space? Yes. So one way you can think about an algebraic variety is just, I mean, in the same way as in algebraic geometry, you think of an algebraic variety given by union of affine pieces. You can do exactly here the same construction. Okay, so that's the first way. The second way that you can define is that now here, I gave the definition of a point of a Berkovich in the Berkovich space as a semi-norm on the function of the field of function that are defined, like this ring A. But there is a way you can define a point in the Berkovich space just by using the point of the variety. So you will replace the semi-norm on the ring A with a norm on the residue field at your point. So this will just, I mean, the advantage of this definition is that it immediately works for all algebraic variety. You don't have to pass through the affine variety and then do a gluing process. So if you're interested in also this definition, this is stated in the problem session. So you will see the details there.